Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on analytical dynamics or classical mechanics, chapter variational principle in dynamics, lecture number 1, in which I will state and prove Hamilton's principle. Now we state and prove Hamilton's principle statement. The motion of the system from time t1 to t2 is such that the line integral I equal to integration limit t1 to t2 L dt, where L equal to T minus V, T be the kinetic energy and V be the potential energy. This integral is an extremum for the path of the motion, that is delta I equal to delta integration limit t1 to t2 L dt equal to 0. Here for delta variation we compare all conceivable paths collecting to given points A and B at two given time. Here time t equal to t1, here t equal to t2, t1 and t2. The system must travel from one point A to another point B in the same time, means difference of t2 and t1 be same time for all paths. The system point is speeded up or slowed down in order to make the total travel time along every path the same, and energy may or may not conserve along the paths. The position coordinates of end points should be fixed. These are the conditions for delta variation. In nutshell, A and B be two fixed points. This system point may travel through any path, but condition is that total travel time must be same. Means time at A equal to t1, time at B equal to t2, then t2 minus t1 be same for all paths. In this process, the energy may be conserved or may not be conserved, and this is the concept of delta variation. Then this I, the integral I, will be extremum, that is delta variation of I equal to 0. Now we prove this. Since by D'Alembert's principle we know that sigma mu under bracket F mu minus P mu dot delta R mu equal to 0, where F mu be the applied force on the muth particle and P mu be the effective force for muth particle. Now total effective force equal to sigma mu P mu dot delta R mu vector equal to sigma mu P mu be the effective force for muth particle, and this will be equal to mass into acceleration. Mass of the muth particle multiply acceleration r mu double dot delta r mu vector. We may write this sigma mu a mu d by dt r mu dot vector dot delta r mu vector minus r mu dot vector d by dt delta r mu vector. Let this is number 2. We know that delta can be interpreted as an operator which produces a small change in vector r mu. It is not connected with the time. It can be treated like differential operator. Both delta and d operators can commute. That is delta dx equal to d delta x and delta dr mu by dt equal to d by dt delta r mu. Since delta variation corresponds to a virtual displacement and not associated with change in time, that is delta t equal to 0. Therefore, equation 2 may be written as sigma mu p mu vector dot delta r mu vector equal to, here sigma mu a mu d by dt r mu dot delta r mu minus r mu vector dot, here delta d by dt r mu vector, and this will be equal to sigma mu a mu d by dt r mu vector dot delta r mu minus r mu vector dot delta, this d r mu vector by dt is r mu vector dot, this equal to sigma mu a mu d by dt r mu dot vector dot delta r mu vector minus delta half r mu dot square, this equal to d by dt sigma mu a mu r mu dot delta r mu vector minus sigma mu delta half a mu r mu dot square. This is number 4. Using 1 we get sigma mu, this is f mu vector dot delta r mu, this equal to d by dt sigma mu a mu r mu dot delta r mu vector minus sigma mu delta half a mu r mu dot square. Let this is equation number 5. Since F mu be the applied force and delta r mu be the displacement, so F mu dot delta r mu, work done, and sigma mu is the total work done, and this will be equal to negative of change in potential energy, V equal to potential energy. Let this is number 6. Again, half a mu r mu dot square be the kinetic energy for muth particle, and sigma mu is equal to here negative of change in potential energy, here gain in kinetic energy, T be the kinetic energy. This is number 7. Using 6 and 7 in 5, we get left side is loss in potential energy, this equal to d by dt, here sigma mu a mu r mu dot vector dot delta r mu vector minus delta t implies that delta t minus delta v equal to d by dt sigma mu a mu r mu vector dot delta r mu implies that delta t minus v equal to d by dt sigma mu a mu r mu dot vector dot delta r mu vector implies that t minus v is L, delta L equal to d by dt sigma mu a mu r mu dot delta r mu vector implies that delta L dt equal to d sigma mu a mu r mu dot vector dot delta r mu vector implies that integration limit time t1 to t2 delta L dt equal to integration time t1 to t2 limit d sigma mu a mu r mu dot delta r mu vector. Let this is number 8. since delta L dt equal to delta L dt plus delta dt, and this will be equal to delta L dt plus this delta dt is 0, since in delta variation we do not consider the variation in time. Implies that delta L dt equal to delta L dt. This is number 9. Using 9 in 8 we get integration delta L dt is delta L dt time t1 to t2 limit, and this is will be equal to integration of this is sigma mu a mu r mu dot vector dot delta r mu vector, here time t1 to t2. Let this is number 10. Since in delta variation we assume that no variation in coordinates at the end points of the path, so delta r mu vector equal to 0 at two end points of the path for every particle. Therefore the right side of equation 10 will be 0, because value of the delta r mu at t2 is 0 and value of delta r mu at t1 equal to 0. Therefore equation 10 may be written as here we may commute this delta with the integration delta integration t1 to t2 L dt equal to 0. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.